Okay, so this is Core Pure 1, June 24 for Edexcel, further maths. And this is question 5, and it's a first order differential equation. They've wrapped it up in a question about a raindrop. Is it a raindrop? Yeah, raindrop falling from rest from a cloud, and its velocity after a certain amount of time. And the first thing we've got to do is solve this differential equation to show a particular expression for v that they give you. We've got a constant here, k, that I imagine somewhere down the question we're going to have to find out. But the thing that we're trying to prove, though, has k in it still, but there's no other constants, so we're going to have to use initial conditions at some point. So the fact that it falls from rest means that when v equals 0, t equals 0, so I'll just stick that up there, because I'm sure we're going to come back to that at some point. Now, with the first order differential equation, a lot of the time it's going to be an integrating factor. And so what you're looking for an integrating factor is basically your differential, so in this case dv by dt, plus v times some function of, in this case, t. So if it's dy by dx, it'll be y times some function of x. Now this t plus 2, we don't want that down at the front. So what we're going to do is divide everything through by t plus 2 first of all, to get it into the classic form where we use a differential equation, integrating factor, sorry. So we're going to divide by t plus 2 on here. That's going to give us 3v over t plus 2. And over the other side, don't forget about dividing by t plus 2 there as well. And you get k minus 3 over t plus 2. Okay, so our integrating factor is simply the thing that we are going to multiply this through by, so that this left-hand side becomes just a straightforward reverse product rule. Okay, and the integrating factor is always e to the integral of the function of t you've got multiplying v here. So we've got, that's not very good t, is it? 3 over t plus 2. So we're going to be integrating that. Well, down on my knees already. The integral of 3 over t plus 2 is 3 ln t plus 2. So that's going to become e to the 3 ln t plus 2, or natural log. I know some people laugh when I use the word ln. We can bring the 3 up there and cancel the logs, so we're going to get t plus 2 cubed. Hopefully we see that happening. 3 comes up there to get t plus 2 cubed. E ln. Cancel each other out if you want to think of it like that. Well, no, we really shouldn't think of it like that, but anyway. We end up with t plus 2 cubed. So that is what we're going to multiply all the way through by, and that will give us a lovely reverse product rule here. So t plus 2 cubed on here gives us t plus 2 cubed dv by dt, plus, times in here we're going to get 3v t plus 2 squared, because obviously we're going to have t plus t cubed cancelling with the t plus 2 there. On this side we're going to have k t plus 2 cubed, and then minus 3 t plus 2 squared. Okay. Now, if we've done that correctly, this is just a reverse product rule of differentiating v times t plus t cubed. V, in this case, or y, or whatever the lead variable is, times the integrating factor. And if you look at that, I mean, I'll put it over dt. If you look at that, if we're differentiating that product rule, the v would differentiate to v by dt times t plus 2 cubed, and the t plus 2 cubed will differentiate to give us 3t plus 2 squared times the v. So you can see that that actually works out. Over this side, we still got our k t plus 2 cubed minus 3t plus 2. I know a lot of people that don't write out that stage, and that's perfectly fine. You can go straight to this line, which is, right, integrating both sides with respect to t, we get vt plus 2 cubed here, because obviously the integral of this with respect to t undoes the differentiating, if you like. Over here, integral of k t plus 2 cubed minus 3 t plus 2 squared dt. So here we go, v t plus 2 cubed equals, integrate this, and we're going to get, let's see, that's going to turn into a quarter, so k over 4, t plus 2 to the power 4. Lovely, t plus 2, so we don't have to worry about dividing by whatever this is differentiated. Here, that's going to turn into, shouldn't that be a, let me just check that, that's a square, sorry. Bad copying from Buff. Right, that will turn into obviously a 3, divide by 3, so it's just going to get minus t plus 2 to the power of 3 plus c. And now all we've got to do is go, right, okay, well we know initial conditions that when t equals 0, v equals 0. So let's put v equals 0 and t equals 0 into here. So v equals 0 into there gives us 0. T equals 0 into there gives us 2 to the power of 4 is 16, divided by 4, so 4k there. T equals 0 into there gives us 2 to the power of 3, so minus 8 plus c. So that means c is 8 minus 4k. So putting that all together, I'm going to rub off this top bit if that's okay. We've got v t plus 2 cubed equals k over 4 t plus 2 to the power of 4 minus t plus 2 cubed plus c, which is 8 minus 4q, plus 8 minus 4q, 4k even. Right, and then check what we want to look at. We want v the subject, so we're going to divide through by t plus 2 cubed. So v equals k over 4, t plus 2, just the power of 1, because we're taking the cubed, divided by cubed. That's just going to become 1. This is going to become 8 over t plus 2 cubed. This is going to become minus 4k over t plus 2 cubed. Let's have a quick look, see if we've got roughly the same thing. We've got that, minus 1 plus, oh, they just put that together and factorised out the 4. So yes, don't make the mistake of not actually writing down the final line. In any show that, they're really pernickety, your final line's got to be exactly what they've got written down there. So let's write v equals k over 4 t plus 2 minus 1, and then let's put these together and take the 4 out. So it's 2 minus k over t plus 2 cubed, which is what they want. Perfect. Okay, so there's your part A done. That means that. 5 marks. A fair bit to do for 5 marks, I think, there. Right, part B. Given that v equals 4 when t equals 2. v equals 4, t equals 2. Oh, it's time to swap the pen. Hang on a second. So we get a nice one that works well. So v equals 4 when t equals 2. I imagine we're going to have to find out what k is. What do we want? Determine, according to the model, the velocity of the raindrop 5 seconds after it starts to fall. So we want what is v when t equals 5, basically. So we're going to stick those into there to find our k. So putting in 4 in equals k over 4. So we're going to have 4, when t equals 2, we're going to have 4 there, cancel there, k minus 1 plus, putting t equals 2 into there. We're going to get 4 cubed over 4, so that's a 16, so it's 2 minus k over 16. I think that's right. Just quickly check. 4 cubed, yeah, 4 squared, yeah, that. Okay, so we've just got to solve that. So let's times through by 16. So we get 64 equals 16k minus 16 plus 2 minus k, so that's 15k. Minus 14 over to there equals 78, all done like that. K equals 78 over 15. So that's 5 1/5, isn't it? Isn't it? Yeah, so 26 over 5. Yeah. Just going to quickly check that I haven't done anything stupid there. Have I got there right? Okay. Yep. 26 over 5. So now we can just put it in to find out what is v when t equals 5. So v is going to be k over 4, so that's going to be 26 over 20. T is 5, so put it in there. You've got 7 minus 1 plus 4, lots of 2 minus 26 over 5 over t is, what is it again, 5. So for 7 cubed. Bang it all in your calculator, and apparently leans over to have a look at the answer. You get 8.06. All done. Right, and as usual, we got a little 1 marker at the end. Comment on the validity of the model for very large values of t. So let's have a look. When we're going to get very large values of t, this term here, big value of t, is going to become virtually 0. However, this term here is going to be huge because it's going to be large value of t. So basically the velocity is just going to continue to get bigger and bigger and bigger and bigger, which is not really sensible. So obviously for large values of t, it looks like there's no terminal velocity. It just seems the velocity is going to get bigger and bigger. So my thing would be it's not valid because it implies the velocity is just going to get bigger and bigger and bigger. Whereas in reality, what it reaches is a terminal velocity. It doesn't get constantly faster and faster. I'll tell you what they've said. Velocity increases indefinitely, which is unlikely. So same thing. Raindrop will reach the ground, doesn't fall forever, so not valid. That's a classic. Obviously, always look for things like, right, does this mean that at some point, you know, in future time, it's not going to fall forever? It's eventually, the clouds not an infinite amount of distance above the Earth. So that kind of idea is always one. You look for things like, oh, well, does it become negative at some point if it's a distance or something like this? Something that's an actual, arrives at a value that is just not valid, just nonsense for the actual model. And then they've said, the raindrop will reach a terminal velocity, thank you, that's my one, after a finite time, so not a good model. There we go. Not a bad question, I think. Quite a bit of work for that first 5 minute marks though.